Can anyone tell me the definition of a derivative? Thank you, Natalia, but I want Natalia to answer, please. Can you tell me the definition of a derivative? No. Are you also confused on what a derivative is? Well, don't worry. Today we're going to break it down. From slope to velocity, tangent and secant line, and even describing differentiable functions. So let's start with slope. Hopefully we recall the equation y2 minus y1 over x2 minus x1. This equation is the ratio between rise and run of a straight line. We can also say that it's the vertical change over the horizontal change between 2 points. Therefore, slope is describing the steepness of a line. Consider these two hillsides. If we wanted to know which of them was more difficult to hike, we could calculate their slopes. Using rise over run, the hill with the steeper slope or the larger slope would be more difficult to hike and make our calves burn way more than the smaller one. Let's say we need to go to the store. The displacement between home and the store we'll consider delta D. The time it took to get from point A to point B is delta T. If we take this example, we can graph our positions when we left home and when we arrived at the store relative to time. The x-axis represents time, and the y-axis represents distance. When we graph these 2 points, these position coordinates, we get a straight line. If we were to calculate the slope of this straight line, what would it tell us? Using the slope formula, we can plug in our numbers and units to find out. Here's a quick algebra review since algebra is so essential in understanding and passing calc. Whole numbers are divided by an invisible 1, and dividing by a fraction is the same thing as multiplying by its reciprocal. So we end up with 32. But please don't forget your units. I have been marked down for this in high school and in college countless times. So let's take a look at these units. We end up with miles per hour. So we've calculated our velocity. So velocity is a rate of change between displacement and time. The SI units for velocity is meters per second, but in our example, we use miles per hour. Quick note for you physics students. While we might use speed and velocity interchangeably, in physics, speed and velocity are not the same thing. Speed is a scalar quantity and velocity is a vector. While our slope formula is helpful to find the slope between 2 points, what if we only had 1 point? Let's consider the point on this curve. If we zoomed in enough, the curve at this point almost looks like a straight line. That means that the curved line around this 1 point can be approximated if we actually draw a straight line at this point. We call this line the tangent line, which comes from the fact that it's tangible to this point. It skims this point. But how do we find the slope of this line? Let's consider a second point on this curve. When we draw a line through these 2 points, we call it the secant line. So now we can consider finding a slope between these 2 points. We'll call the first x-coordinate x. The second x-coordinate, though, we don't quite know yet. So we'll call the horizontal distance between these 2 points delta h, and therefore the second x-coordinate we'll call x plus h. The y-coordinate of our first point is f of x, and therefore the y of the second coordinate is f of x plus h. So now, with these 2 points, we can find the slope of our secant line. Using our slope formula, we'll plug in our coordinates. And with a little process of elimination, we'll end up with f of x plus h minus f of x all over h, the slope of our secant line. So how does this relate to the tangent line? Well, if we were to move our second point closer to our target point, closer to the orange point, our horizontal distance between these 2 points has gotten smaller. If we continue to move the second point closer and closer to our target point, our delta h becomes smaller and smaller. If you were to draw a point so close to the target orange point, the secant line between these 2 points will basically look like our tangent line. The delta h in this case would be getting so small, infinitely small, that it is approaching 0. Here's another visual representation. Let's say you scored a home run in baseball. I know a lot of us miss our sports. As you're running towards home base, your horizontal distance between you and home base continues to get smaller and smaller. On the graph, U represents the purple point and home base is the target orange point. Since you're getting closer to home base, delta H gets infinitely small. We'll say that H is approaching 0. I'm hoping the phrase H approaches 0 makes you think of limits. Now, I'm not saying you're going to like the thought, but this phrase does represent a limit. So, if we were to take the limit as H approaches 0 of our secant line slope, we'll actually be calculating the exact slope of our tangent line. If you're still with me, we have finally made it to the definition of our derivative. The derivative is a rate of change at one instant. It is our tangent line at one point. The rate of change is represented by the second part of this equation, which we found from the slope of our secant line. The first part, or the limit, comes from the fact that we're trying to come to one instant on the curve, found when H is approaching 0. There are different notations for the derivative. We can call it f prime of x or y prime. You'll definitely see it as dy over dx, which comes from our change of y over change of x. And we can also see it as d over dx of f of x, or the derivative of this function. Okay, so now that we know what a derivative is, let's talk about differentiable functions. Differentiability implies that the limit coming from the right and left side at a point on the derivative equal each other. In other words, it's describing the continuity of the derivative. Okay, so let's take a look at this theorem. It states, if a function is differentiable at point A, then f is continuous at A. If you use your pencil to draw over the curve, and if you never have to pick it up, then your function is continuous. But let's use this example. I have to pick up my pencil to continue drawing over it. This is called a discontinuous function. In this case, we have what's called a jump. I do want to give you a warning on this theorem. The converse of it is false, meaning if we switch the if part of the statement and the then part of the statement, it is not true. Let's take the graph of the negative absolute value of x, which is continuous. But if we look at the top, we have what's called a corner. The way I like to think about it is if I were to take my pencil at that top corner, I don't have a smooth curve to know how to draw my tangent line. However, if I did have a curve, then I would know how to draw the tangent line at that point. Basically, tangent lines and corners just do not go together. But if that didn't make sense, no worries. Here's the proof. This is the piecewise function describing the graph of the negative absolute value of x, and we also have its derivative. At the corner point, we don't know what the derivative is since the left side and right side don't match, and it creates a jump. And remember, differentiability implies that the limit coming from the left and right side at the point on the derivative are the same. Therefore, this point on the function is not differentiable. Here's another example when the converse is false, a vertical tangent line. Although this is a continuous graph, its tangent line has an infinite slope or an infinite discontinuity. Therefore, since the f prime of x, or the derivative at this one point, is discontinuous, then this point is not differentiable. I hope you found this helpful. Let's try to be patient with ourselves when learning anything new. It can be difficult at first, but hang in there. Question of the day. I know finals are coming up. You might be taking this class in the summer. So what's the next calc or math topic that you'd want to cover? Let me know down in the comments below. Have fun studying, stay curious, be sure to subscribe, and I'll see you next time.